Hello everyone, I'm Xu Rongchen from Tsinghua University. I'm glad to show our recent work on data-driven termination analysis. The termination is a crucial liveness property for a program. A lot of work has been devoted to the analysis of program termination for a long time. However, termination analysis is still challenging. Essentially, it is a hunting problem for Turing machines, and it is undesignable. With the development of machine learning and data science in decades, the data-driven methods has been applied to many fields, including program verification, and it has shown its unique advantages. In our work, we attempt to integrate data-driven approaches with the termination analysis of a program. We guess a loop bound for the program loop based on a set of execution information and keep refining the loop bound by constraint solving until the termination can be proved. Let's introduce the concept of loop bound first. Look at the right program with a single loop. In the loop, the variable x keeps increasing when it is less than 10. Otherwise, it will be reset to 0. Obviously, the program is always terminating. But how can we strictly prove it? So we introduce the loop bound. For all input x, we can find that the loop must iterate no more than mx equals max negative x plus 11 or 1 times. We call such the m a loop bound for the loop. If we can find loop bounds for all the loops in the program, it's easy to prove that the whole program is terminating. This is a main framework of our loop bound learning and refinement for termination analysis. Initially, the default loop bound m equals 0, and the data set for bound learning h is empty. In the analysis, we will generate a verification task for current loop bound m and check whether it is valid. If the current bound m is valid, we can easily report the program termination. Otherwise, we can produce a counterexample during the validation checking and update the dataset h. Then we can learn a new bound and repeat the procedure above. In the framework, there are two critical problems. One is how to learn a loop bound, and the other is how to check the loop bound. We will further discuss about them in the following slides. Output trace, which is produced by the print statement. The output trace records the program states about variable x and the counter j. Suppose the subscript is from 0 and the trace ends with xk. That means the loop finished after the xk. Let's define an iteration down counter IDCI for each xi. IDCI equals k minus I plus 1, which represents the remaining numbers of iterations before the execution terminates. By combining each xi with its iteration down counter IDCI, we can get a data example. Suppose H is the data set for data examples. Thus, we can formally define the loop-bound learning problem is to find a loop-bound candidate M, such as for all data example X, IDC in the dataset, MX is always greater than or equal to IDC. Now, let's consider if already given a loop-bound M, how to validate it. Our approach is as follows. Firstly, we instrument assume command before the loop, which ensures the validation counter I is greater than or equal to current bound candidate initially. Secondly, at the top of loop bound, we instrument assert command, which requires the validation counter I is always greater than 0, and an assignment command, which makes the validation counter I decrease 1. With the instrumented code above, we can transform the termination proof into a safety property check problem. If the safety property in the transformed program is valid, it means the current loop-bound candidate is correct. Thus, we can easily conclude the termination for the original program. Otherwise, if the transformed program is not valid, we can get an error trace violating the assertion statement as a counterexample, which starting from x0 and the trace goes through the loop iteration at least m(x) times. We treat the validation task with an off-the-shelf safety property checker, which is based on a data-driven loop invariant synthesizer. Remember, the loop invariant synthesizer is also data-driven. In the later slides, we will discuss a data sharing mechanism between the safety property checker and the loop-bound learner to speed up the termination analysis. Let's begin with a concrete example to show our ideas about loop-bound learning. Recall that our loop-bound candidate always starts from 0. With the mx equals 0, we generate the validation task as the program showing in the red box. Actually, the loop-bound mx equals 0 is not correct. The safety property checker can return an error trace, which starts from x equals to -2 and the validation counter I equals 0. The error trace violates the assertion immediately at the first time entering the loop iteration. The information provided by a single data example is always limited. Actually, we found that the program states near the error traces may also result in the violation of the assertion, and often have a similar reason for the error. So, in order to get more examples in one term, after we receive the error trace, we make a mutation test near x equals 2. Then we can get the following data set, which is labeled by triangles in the figure. Here we can apply a simple loop-bound learning strategy, and we can get the loop-bound candidate for the next round, which is m equals -x. Our simple loop-bound learning can be reduced to an optimization problem. Suppose the template for the simple bound is a fan function, which is in the form of the sum of ai times xi plus ai plus 1, where each AI is a coefficient, and each xi is the program variable. The optimization constraints ensures the bound candidate could cover all data examples in dataset. The optimization target contains two main targets. The first one is vcost. Vcost encodes the square distance between the bound candidate and the data examples, which makes the candidate's result close to the actual number of loop iterations. The second one is mcost. Mcost is a square sum of coefficients, which makes the candidate's result prefer a simplified format. Here, both alpha v and alpha m are two hyperparameters. Let's continue our loop-bound learning and termination analysis. Now the bound candidate is m equals minus x. As same as the first round, we generate the validation program in the red box. Actually, the bound candidate is still invalid. We can get an error trace from the safety property checker, which starts from the state x equals 1 and the validation counter I equals 0. The error trace violates the assertion immediately at the first time entering the loop iteration. Again, we make a mutation test near the trace and get the new data examples, which are labeled by diamonds in the figure. Now the data examples has been extended, and the dataset has includes triangles and diamonds. Different from the first 10, we found that a simple loop bound cannot fit the dataset tightly. In order to avoid the loss of local features, we apply a conjunctive bound learning here. Our conjunctive bound learning will use a clustering algorithm to convert the conjunctive bound learning problem into several simple bound learning problems. In our example, the dataset can be clustered into two subsets. One is the red cycle, and the other is the green cycle. By applying the simple bound learning independently on each subset, we can get the conjunctive bound candidate for the next round, which is mx equals max minus x and minus x plus 11. After receiving the new bound candidate, we began the third round of bound learning. Now the bound candidate is mx equals minus x and minus x plus 11. Similarly, we call the safety property checker to validate the bound candidate. However, it is still not correct. We can get an error trace from the state x equals 11 and the validation counter I equals 0. We make a mutation test near x equals 11, and we can update the dataset with new pentagons. By applying the clustering algorithm, we can get three subsets. They are the red cycle, the green cycle, and the orange cycle. We can learn the loop bound for each subset independently. Notice that in the subset with the orange cycle, to get better local features, we apply a technology that allows some examples not covered by a single simple bound, such as the leftmost data examples here. Thus, the orange subset can learn two simple bounds, minus x plus 11 and 1. By combining all the bounds from each subset, we can get the bound candidate mx equals minus x plus 11 and 1. In the end, we can remove the redundant bound minus x by using a bound combination technology. The technology is based on a set covering algorithm and can reduce the difficulty of the bound validation. Finally, we can get the bound candidate for the next round, which is mx equals minus x plus 11 and 1. The bound candidate in the first round can finally pass the bound validation. Thus, we can conclude that the bound candidate is a correct loop bound and the original program terminates. Apart from the simple loop bound and the conjunctive loop bound, our work also considered another loop bound called lexicographic loop bound, which has a stronger ability and can handle more complex situations. You can read our paper for more. In our example, we use 4 rounds before we found a correct loop-bound candidate. Usually, we need a considerable number of rounds before a correct loop-bound is learned. During the bound learning procedure, we can find that in most rounds, the bound candidates are refined by arrow traces provided by validation checker. And only in the final round, the validation checker will make a proof. As we know, founding a falsified model is always much cheaper than verification. We thus design a BMC-based quick bound checking strategy. According to the quick bound checking, the validation task will proceed with following 3 steps. Given a predefined key, we will check whether the program is still feasible when unrolling the loop k times. If not, the program obviously terminates. Otherwise, we will go to the second step. Given a predefined key, we will check whether the bound candidate may be validated after unrolling the loop k times. If so, we can directly return the arrow trace. Otherwise, we will invoke a loop invariant synthesizer to check the safety property exhaustively. Recall that our safety property checker uses a data-driven loop invariant synthesizer for bound validation. Since both the bound learning and bound validation are data-driven, we can make full use of the similarity between the bound examples and the invariant examples. We thus designed the following two-way data sharing framework here. In our design, each bound examples can be transformed into 2 invariant examples, which can speed up the validation process. Also, the invariant examples can revolve an arrow trace. We use them as a seed for mutation tests, which can speed up the generations of bound candidates. According to our technologies, we implemented a prototype tool called ddlTerm, which is shortened for a data-driven loop termination analyzer. We compare our ddlTerm with 4 state-of-the-art termination analysis tools. There are frequent-term, ultimate optimizer, approve, and mover. Note that there are 3 different backend constraint solvers for frequent-term, so it has 3 configurations. Our benchmark contains 170 terminating programs. The timeout setting is 120 seconds. Here the table shows the overall results. Our ddlTerm solves 136 benchmarks, and the average solving time was 5.43 seconds. Our tool solves 13 to 48% more benchmarks and saves 40 to 77% solving time compared to other tools. Here are some detailed results. We compared our ddlTerm with baseline 1 by 1. In this figure, each point is a benchmark. The x-axis represents the solving time of ddlTerm, as the y-axis represents the solving time of each baseline. The second figure is the cumulative time for solving benchmarks. ddlTerm extends further because it solves more benchmarks and grows more slowly in the cumulative time. From these figures, we can clearly see that our ddlTerm outperforms other tools. That's all of our presentation. Thank you for your listening.